and where the computer might crash in the middle using various techniques like logging. And then if we have time, I'll come back and tell you guys about some of the ongoing open problems in what we've presented to you guys, some assumptions, and how you might go about modeling them and dealing with them. All right, so to start off with recovery again, I want to recap the execution model that Franz showed you guys yesterday, where we were concerned with situations where we might execute normally. So for example, you have your code level states, and you're executing normally, going through several states over here, and eventually end up in some sort of a final code level state. And this is all well and good. This is handled by pre and post conditions that we looked at. But at any point during the execution, you could take any of these code states and your computer might fail or crash. And after rebooting, it'll enter recovery code. So from this state, you might unexpectedly transition to recovery code and start running recovery over here. So this is the regular implementation of whatever operation we are talking about. At any point we crash, go into recovery. At any point in recovery, we might crash again and then go into more recovery, and so on. And the problem for us was to somehow reason about all these different executions. And the kind of reasoning we want to do is to correspond these code level states with specification level states. So spec states start out in some initial state 0, and ideally we are executing an operation that should get us to a final spec state SF. And the correspondences between these code states and spec states are a little bit tricky. So first off, we should talk about final states in this code level diagram. So these are intermediate states, and here's the only place where we actually got to a state that we care about. We finished execution. And recovery also sometimes finishes. So for example, here is a possible recovery trace where we ran, and recovery really got to the end without crashing some more. So this is a terminating state of recovery, and here's another possible terminating state of recovery. And you can imagine there's many other possible such terminating final states. So the question is, what should the correspondence be between these code states and the spec states? Of course, the initial state, I'll draw this correspondence by yellow, these guys correspond. And if you reach the end of the execution without any crashes, yeah, you should probably correspond to the final spec state. And what our framework requires is that all these recovered states, if you crash and recover, they don't have to actually roll back all the way back, because maybe you can't roll back if you crash far into the execution. And they don't have to be necessarily the final state if you crash too early. You haven't actually done anything. But they do have to be one or the other. So this is what we call before or after atomicity. So every one of these states where recovery eventually finishes must be either the final state here or the initial state. And as part of the proof, we get to sort of choose which one did we actually happen to hit. And if we can show either one, that's good enough to show the safety property that we care about. That make sense? All right. So the problems that we're dealing with here is that we have these infinitely many executions. So unlike in the previous case where we had these well-terminating programs, they all ran to completion, now this infinite set of executions really comes from the infinite set of crash points and recurring crash points that you might encounter during the trace. Yeah?
So when you finish the recovery and are in either S0 or SF, would you also be in C0 or CF?
Not necessarily. It might be that after recovery, there's a counter of crashes on disk, and you bump this counter for statistics purposes. So it's not going to be literally C0 or literally CF. You might be in a state that you would never reach if you never crashed. But it is, to the higher level software, it appears just like S0 or SF would. Make sense? Yeah?
So should we consider C0 to CF as a single procedural routine, or should we consider C0 to CF as a whole program execution, or what's the granularity of the step on S0 to SF?
So the granularity depends on the layer of abstraction that you're considering. If you're talking about application level software that sits above this layer of specification, you don't want to look at the details. And this is exactly why it is important that recovery not expose any intermediate states. Recovery should be clean. It should go back or go forward. On the other hand, if you're in the midst of implementing this module, you really have to look at the detailed steps at the code level that this implementation takes, and you sort of expand it out, unfold maybe in Coq terminology to really look at this, and you drop down the abstraction level, of course, because you can't even represent these intermediate states in the code using specification level abstractions. There's no spec level state that corresponds to these middle points because it's not a clean state. Make sense? Hopefully it answers a little bit. All right. So the problem we're facing are these infinitely many executions. And as Franz alluded to yesterday, the proof of correctness for us is going to rely on idempotence of this recovery routine. And idempotence means that you can take this recovery routine and keep re-entering it as many times as you want. And if you ever reach the terminating state of recovery after many crashes, it'll be an equivalent state to as if you finished right away with no crashes at all. So we'll see this formalized in a second. And the way we're going to really deal with the infinity is very much like how we deal with infinities in loops, using a loop invariant. So we're going to be stating this thing called a recovery condition, which is going to be a predicate on states that describes all the states that we might encounter during recovery. And at least at an informal level, you can think of it kind of like a loop invariant, where you have this infinite loop of crashes, and this loop invariant holds at every iteration of the loop, and eventually you exit the loop when you stop crashing. Make sense? Questions? All right, so one thing I want to show you guys is how we represent this picture that I showed on the left here in Coq terminology. How do we model normal executions going forward and these crashing trees of many possible executions where you go into recovery? So here's our definition of execution semantics. This one is not terribly interesting. The only interesting thing that you should pay attention to is the type of this relation. This is an execution relation that tells us how to take a program that supposedly returns a thing of type T and describes how it executes, starting from some kind of a world state and producing a result. So what are these results? So this result is defined up here. It is either a finished result, where the program reached the state CF, and the result contains both the value that the program is returning and the new state of the world here, denoted by W. Or the result of running this implementation program might be one of these intermediate states, in which case there is no return value. There's just a new world state in which you crashed. So that's the model for modeling a sort of single-shot run of a program. And then we're going to model this sort of tree-like structure up here of rerunning recovery many times. So let me show you the relation for that. Here's the relation of exec recover. So this models taking recovery and running it as many times as needed to get to a final state. So to look at the signature of this guy, it's going to take our recovery procedure and a world state where we start. So this is the world state that we're talking about in this relation. And this relation is going to give us R, which is what the recovery procedure eventually returns when it reaches one of these states, and the world state, the state of the system where the recovery is going to leave us. And the way we define it is we say, well, you could either run recovery straight up and get lucky, and recovery finishes. That's cool. That'll get you to a new state. So that models this branch through my diagram, where you don't crash during recovery. Or you might try to run recovery, and the sort of single-shot execution of recovery gives you a crashed world state. In this case, this is modeling the case where you try to run recovery, it crashed in another state. Well, we're going to pick it up and do the same thing all over. This is the recursion going back to the same exec recover relation, starting now from a different world state, this W prime, where the recovery crash left us again. Yeah?
This means, since it's inductive, that you eventually will recover.
So a statement or a proposition of type exec recover is a statement that, yes, recovery finally finished. We don't have a theorem that it necessarily will finish for any given sort of execution, but there are arbitrarily long executions that do eventually finish.
So does this mean you can not reason about liveness properties?
You fundamentally don't have liveness. If you do, like, my laptop runs out of power and I never plug it in, there's no liveness. Yeah. Yeah. Other questions? Okay. So the final thing that we're going to do, so now we have this exec relation that we model here, and this exec recover relation that models the repeated attempts to run recovery. We can tie them together in this recovering execution relation, rexec at the bottom here. Question?
I think I'm not satisfied with that last answer because I understand fundamentally my laptop may never execute again if you install a battery. But if you put the battery back, I might well like to know that under the assumption some underlying failure has been recovered from, that the upper layers of recovery are live.
Yeah, sorry, I had a slightly flippant answer. And actually, this is slightly incorrect also. The real situation that is not live for us is that my laptop, I keep trying to charge it and tripping over the power cord, charging and tripping again. That's the thing that's not live. But you can imagine that in the absence of liveness, all of our Galena programs are actually terminating. We have a co-inductive definition, but it's not really used in the interesting things about which we prove theorems. So in the absence of failure in the exec relation, all the Galena programs themselves are terminating Galena expressions with these little opcodes for disk I/O. So if you introduce some kind of an axiom that says every disk I/O will return, then by sort of construction, all the Galena programs will eventually finish executing as well, with some assumption about execution. We haven't bothered to try to formalize this and prove this, but at least in the current construction, plausible if you really wanted to make these assumptions. Yeah. Sense? Other questions? Okay, so this rexec relation that I was going to show sort of summarizes this whole diagram and gets us to the point where we can draw these nice sort of yellow arrows and ignore the transition mess in the middle. So rexec talks about, if you look at the type signature, it takes actually now two programs. It takes the program that you're going to try to run and hope for no crashes, and it takes another program, which is the recovery procedure. And this rexec relation is going to take a world state where you start C0, and it's going to give you a recovery result, R result. So let me show you what that is. It is one of these two guys. It's kind of similar to the result we had for straight line executions, except that it's going to tell you whether you finished like this or you recovered like that. And in both cases, it's going to give you a state where you ended up and a return value from either your normal implementation or from your recovery procedure. And this rexec relation that we define is going to look fairly similar, hopefully not surprising. We try to run it, try to run the program. If it finishes, we finish. And if we crashed, then we keep trying to run recovery using this exec recover relation you guys saw. And if so, we declare success with the recovered outcome. Make sense? Any questions? Okay, so that's our way of representing these trees of executions. And now we're going to try to actually prove some theorems about them. This is what we assigned to you guys to prove. So let me show you the implementation of the recovery code that we asked you guys to prove, and then sort of draw some diagrams about what I think our proof structure is going to look like. Question?
Why do you need to distinguish between recovered and finished?
Because in the case of finished, you must draw this yellow arrow, and then the recovered outcome, you get a choice of these two yellow arrows. All right. So in the implementation we guys gave you, here's the code for recovery. Let's see. It's a large file. So roughly speaking, here's what the recovery code looks like. We're going to see how big the disk is. And depending on how big it is, we're going to run this recursive procedure to try to fix up the disk by copying the contents of one disk to another on any sector that is mismatched. And we know there is exactly one sector, so we'll go up until we hit that one sector where there's a mismatch, copy it over, and return. So the sort of very abstract level sort of diagram of execution is going to be, we're going to start out in some state C0, which is what we want to fix up. And this C0 is actually, maybe I'll call this guy R0. And for clarity, I'll tell you guys this is sort of R0 for me. And we'll keep running recovery. So this is where we're sort of describing our execution. So we start with R0. As you can see on the screen, first we run disk size to figure out what's the size of our disk. And then we run this recover at routine. And our goal is to show that after running recover at, we're going to be in good shape. And if we crash, we can actually keep running recovery as needed by idempotency. So if you remember from last lecture, the way we're going to do these proofs is using Hoare logic, which requires us to state pre and post conditions about the little pieces that we're looking at and use them to compose the proof of the bigger routine. So this is basically going to be an illustration of how to use Hoare logic in this particular case where you have crashes and recovery going on. So if you remember, we need to fish out our lemmas about the Hoare logic statement about disk size and recover at. So let's find a lemma about disk size OK. So here's a lemma about disk size correctness. The precondition of this guy says something about disk 0 and disk 1. This is the precondition. And the postcondition basically says it's all the same things, and something is true about the return value. It's the size of the disks. So that seems reasonable enough. Now let's find the lemma for the recover at routine that we're going to use. This one has a slightly different shape of a precondition. This is using this notion of a state, the conceptual logical state of being either fully in sync or out of sync on a particular address. This is something that Franz showed yesterday. So the recover at precondition is in terms of this, fully synced or out of synced representation. And it transitions and tells us that for each of these states, here's what's going to be on disk for you. If you're fully synced, it remains fully synced. If it's out of synced, we'll fix it up and make it in sync. All right, so these are the two building blocks we have to work with. Now let's go to the recover proof and actually prove that the recovery routine satisfies its specification. So specification for recover here, we can sort of mirror it on the board. It's a little bit long, but it's also in terms of these logical states, whether something is fully synced or not. So the precondition for the big theorem we'd like to prove is starting from a state that's either fully synced or out of sync. We're going to run this, and the post condition is going to look quite a bit like, and the recovery condition are going to look quite a bit like the recovery and post conditions of the recover at, where they're also stated in terms of, well, if you're fully synced or out of synced, that's where you end up. So if we try to step through the proof, what do we get? Well, let me pull this up for you guys. At the bottom here, you can see the proof state, and I'm going to unfold and sort of step through. So what we've done just now is we've decomposed our recovery procedure here into its two pieces, disk size and then calling recover at. And then when we try to call step, what happens is that we end up with a messy goal because it actually, the automation couldn't match up our state stated in terms of these either fully synced or out of sync things with the precondition of disk size. And we have to prove this implication. So in order to make this implication proof go through, we really have to destruct this status variable and consider the two cases. In which case, the proof works out much better. We're able to instantiate and sort of specify what these D0 and D1 are, and the step works out fine, and then we can finally step through the recover at. So all I'm sort of illustrating to you guys is that in order to make this proof go through, you really have to line up the pre and post conditions. And with the one messy point that our automation doesn't deal with is when you state your predicates in slightly different forms. So the predicates for disk size were literally in terms of here's what's true about D0 and D1. And the predicates for this guy were in terms of this more abstract thing saying, well, there's two cases, fully synced, not synced, and if so, they have their own statements about the disk. So if you destruct them, you decompose this bigger thing into smaller pieces that look like this, then the implications work out. And then we sort of, this implication also, you have to consider, you have to sort of consider the two cases. You have to specify which of these two cases you think you are in to satisfy it. And finally, this implication works out fairly straightforwardly. So it's probably not super interesting to step through the details of this proof. It basically boils down to the shuffling of expressions to make these representations line up. So the next thing I want to show you guys is the proof of the idempotence of recovery. So what the lemma that we just proved is the sort of straight shot, single execution of recovery, where we start from a recovery state and we reach some final state if we get lucky, and otherwise we have a description of all the intermediate states where we might crash. So now what we're going to prove is a different theorem called, in our case, prog-loop-spec, that is going to, we'll use in a second to prove something more interesting. But this prog-loop-spec is going to require that this recovery routine be idempotent. And logically, what you can think is that the state anywhere in the middle of this execution, so the recovery conditions of all these little lemmas that we used, they must all imply back to our precondition. So we can re-enter recover if need be. And there's actually another subtle goal we'll see in a second where we have to require that not only can we re-enter recovery, but when it eventually finishes, its postcondition that it's going to establish is what we were promising to establish on our own. So let me unfold these definitions for you. So this statement, goal of prog-loop-spec, says the recover code satisfies this recover spec in a looping fashion. So if I apply a lemma that we have for this, what we're going to see, so idempotent loop spec. So this prog loop spec is a statement about sort of re-executions of this routine. We have a general purpose theorem that says you can prove the repeated re-execution of recovery under two conditions. So here's the two conditions if you apply this lemma. First of all, you must prove that the recovery procedure on its own satisfies this specification. And this is the theorem that we just proved with you guys before, where we say precondition, postcondition, recovery condition. So this one we can apply the recover OK lemma we just proved a couple of minutes ago. And the second condition that our general lemma requires is that this recovery spec actually be idempotent. So this means roughly what I drew on the board. So let me unfold this and show you guys what it's saying. So it says that if you satisfy the precondition in some state, then for every recovery condition, meaning for every point where you might crash in the middle of executing your recovery procedure, then, first off, you can satisfy the precondition of the same specification again. This is this fat back arrow I drew for you guys. And this is the last somewhat subtle issue. It says that the postcondition of recovering from this second execution of recover must imply the postcondition of the original recovery. And what this means is that you can't change these sort of existential variables, if you will, to allow the subsequent recovery to do something else. It might be safe to run, but it'll establish a different result. And this last condition ensures that when you re-enter it, you're committing it to establish the same outcome, if it ever succeeds, as you would have if you succeeded. Make sense? All right, so this proof also turns out to be fairly mechanical. The interesting things that are happening here is that we are breaking down case analysis into whether we crash in a fully synced or out of sync state. And for every one of these states, we have to specify whether re-executing recovery is going to enter it in a fully synced state or an out of sync state. And in most of these cases, it's actually fairly straightforward. The only interesting case is when the initial recovery basically got done. Now it has two disks and both are updated. And this is now a fully synced state, except both disks have this upd expression in them. And this is one subtle case where we have to basically reinstantiate these variables differently. So when we re-enter recovery, the disk is fully synced. This is the exist statement I have up here, but it's fully synced in this new disk state. It's not on the original disk, but it's an updated disk. And what we're proving here with intuition is that, in fact, that's OK. It's going to lead to the same set of post-conditions. So that's the proof of idempotence for recovery. And all of this is basically in service of proving that we can run a procedure like writing to a replicated disk up here and recover with this idempotent recovery that we just proved and prove all those yellow arrows up there. So let me move down to this specification for write. This guy right here. The specification itself hopefully makes sense to you guys. We start with a precondition where the disk is in sync. If we finish, then the disk is in sync on the updated disk state. And if we crash and eventually recover, then the disk is either the old one or the disks are in sync on the new state. This is the clean abstraction that we are sort of going for all along. And what we're sort of talking about is the execution of write, the implementation of this mirrored write, with our recovery on every single crash. And the way we're going to have to do this is by using a lemma, the general purpose lemma that we have that allows us to compose the recovery with a regular procedure. And maybe before we sort of try to understand the Coq formalization of this, I'll draw you out a diagram of all the implications that are required to satisfy using this general purpose lemma. So what we're going to be talking about is, use the stick to give me more board space. So what we're going to be talking about are basically two statements of correctness about the executions of write and the executions of recovery. So for executing write, we're going to start with this code state C0, execute along, and have a final code state. This is the execution of write. And write has its own precondition, some sort of a recovery condition in the middle that describes how it crashes but doesn't really recover in this idempotent way yet, and a post condition. And we're going to compose this write with our recovery. And the recovery, if you sort of, this is just mirroring the diagram at the very top of the boards, starts in some recovery condition state, runs along, and reaches some recovery final state eventually with loops. So I'm not going to draw the loops. The sort of loops are implicit in the execution here. And we have a theorem that we just proved about the idempotent re-execution of this loop as many times as we want. And that statement had a precondition and a postcondition. And it turns out, for reasoning about these recovery loops, we don't need the crash condition or the recovery condition in the middle because it is never exposed. Whenever recovery crashes, it re-enters itself, so the only relevant conditions are the precondition and the postcondition. So these are the two lemmas that we have to work with. And what we want to show is this yellow sort of correspondence to the diagrams above, where we sort of match up to a spec state. But first off, sort of the lemma we're looking at, we're going to establish initially a pre, post, and a recovery condition here. So we'd like to have some sort of a logical state. So maybe that's, instead of states, really, this is sort of the overall precondition, and then we're going to have an overall recovery condition and an overall post condition. So this is for the sort of composed execution with recovery. And then after this, we'll take these conditions, these three conditions, and match them up to the S0 and SF states above with these yellow arrows. So let's think about what actually has to be true in order for us to compose all these pieces together. So the overall precondition must imply the initial, I'll use this wide arrow for implications. So this must imply, so that we can enter the procedure in the first place. Probably is the case that the post conditions must imply so that we can exit and satisfy that we did the right thing. If recovery ever finishes, the post condition of recovery must imply the overall recovery condition. And we must prove that if we ever jump from recovery here to recovery, if write crashes in its recovery condition, enters recovery, we must prove that the recovery condition of this lemma satisfies the precondition of this lemma. So these are the 4 arrows that we're going to have to prove in order to use this lemma that I'm proposing. So I apply this lemma. It requires us to supply 3 things. One is this lemma about the execution of write, which we proved in homework 2 days ago. This is the lemma about the execution of recover, which we proved in last night's homework, or on the board on the screen now. And now we have this combination of the 4 fat arrows I drew on the bottom, implying that the precondition implies the precondition, implying that the post-condition of the whole execution implies the post-condition of the overall spec, implying that our recovery condition implies the precondition of recovery, and implying that the post-condition of recovery here implies the overall recovery condition of our spec. So the proof sort of goes through, you consider all the cases, and it's actually fairly straightforward, works out, because they're already stated in very similar ways, you just have to sort of get the symbols lined up. All right, so that hopefully gets you an end-to-end theorem now that if you run this right and you keep recovering, you'll meet these nice pre-post recovery conditions, and I'm not going to bother showing you that, in fact, these conditions that we showed you satisfy those yellow arrows to the spec state, but those are pretty, hopefully, intuitive to see. Make sense? Any questions about this stuff? All right, well, if not, I'll let Franz tell you about how to actually use such disks now. No screens? Yeah, no screens. Oops.
Well, idempotent. You do it as many times as you like. You know, it should work out. Okay, so what I want to do is sort of follow up on the discussion that we had when we were talking about crash conditions and recovery conditions. And we sort of discussed, like, what do you do with a top-level write spec where basically the write after a crash can either be in the initial condition or in the after condition, right? So we're running write, computer crashes, we come back up, we run recovery, and now the disk is in the state, and the state is either what happened before the write or it actually happened to complete the write. But how do we tell? Right? That was sort of the question that was on the table. And the answer sort of in some ways is it's up to the application to figure this out, or the user of the disk to actually set it up in a way that they can actually tell later what actually state they are. Right? And so what we want to do a little bit is sort of think about like how you use a disk that has this specification that under a failure it can either be in the initial state or actually be in the completed state. So that's the point. And so and what I'm going to show you, or what I'm going to talk about, is basically standard techniques, for doing that. So I'm not going to describe any novel techniques. I'm just going to show you how people that build storage systems, how they deal with those cases, correct? And our main goal, what I would like to do is, as we sort of discuss how people actually, how file systems or databases deal with these cases, try to identify, okay, what are the crash conditions? What are the post conditions? What are the recovery conditions? Is the recovery idempotent? So that you sort of see how that sort of fits in the framework that we've been talking about. So to do that, to make it actually interesting, I need an example. Because like a single write, there's nothing interesting to say about it. We want to basically put a couple of writes and reads together, right? And so I'm going to use the classic example for these kinds of things, which is called, is a transfer, bank transfer, from an account A to an account B, and with some money. And so the basic program for this, correctly, is you read, A, you read B, And then you write the new values to the bank accounts, write A, V0 minus N, so we deduct some money from A, and we give the money to B. All right? So that is our transfer. And then we want to be able to reason about it in the scenario that, for example, we crash between these two writes. Right? So our write specification says, like, well, you could be in before the state of this write happened, or you could be in the state that after this write happened. Right? And so after recovery, you have to do something. Right? Okay, so now there's a couple of small little points I want to make before jumping in. We're going to just assume there's no concurrency, so there's no two transfers running at the same time. There's a separate set of techniques for doing that. So it's basically straight execution, one program executing these things. That's one. Two, I'm going to make another simplifying assumption. So if we're, or compared to what we've done so far, here's our computer, correct? Here's our computer, here's our disk. And, there's two accounts on the disk, and we're just going to think about these as disk blocks, so there's no abstraction really going on, so there's a block, if we model the disk again as an array, as we have been doing, there's a block that corresponds to A, there's a block that corresponds to B, right? This disk, might be implemented using the replicated disk that Nikolai's implemented, but this is just a logical disk at this point, so it's just a single disk from the perspective of this program, right? Because the write, internally, it might actually write multiple physical disks, but at this level of abstraction, we don't care about that anymore. And so we have basically a logical disk with two accounts on it. Okay, let's assume that the accounts start out in the values 2, 20, and 30. Okay, and so for the rest of the discussion, I'm just going to assume actually that there's only one physical disk anyway. Then I don't have to say every time, well, this is a logical disk, this is a physical disk. Just assume one single disk. It doesn't really matter. Okay? Good. Well, so this is our sort of situation setup, and our job, is basically implement transfer in some way. That we're actually doing. We're actually ending up with a bank account where the money is not deducted twice. In the case of a crash, or not added twice, maybe adding, B might be very happy if the money gets added twice, but that's presumably not, A doesn't want to see that happen. So let's start with the naive plan just to see, what goes wrong. So the naive plan or wrong plan. And this really boils down to like, how do we actually implement write? Do we call, the write directly, or do we do something differently? And so let's just assume that this particular write actually corresponds to actually the write that we've been talking about, namely updating the disk directly, as actually sort of been indicating. So we can think about this plan as the update in place plan. Okay, so let's go with that plan and see what goes wrong. So there's two possible cases, correct? The case that we need to consider is whether there's a crash or not. And if, so let's first do the case there's no crash. So that hopefully should be totally trivial, correct? So what's going to happen? We're going to read the two values. So V0 is going to be 20, V1 is going to be 30. We're going to write, let's say we're doing this transaction or this transfer using the value 10. Then, afterwards, we're going to update A. Right, so we're going to make our disk is going to change. 20 is going to go to, let me run a new disk just so that you can remember what the values were. Okay, so we're going to update the disk, to 10 because we're deducting 10. We're going to do the second write, no failures, so things are going great. So we're going to have 40, right? And that's a desirable, good outcome. Then, okay, so the second case is when a write happens. So let's say, there's only one really interesting case, which is like the first write succeeds, and then we crash, right? So at that point, computer stops working, and the transfer just is incomplete, didn't finish, and that's the end of the world. Okay, so let's go for that scenario. So I'm going to erase these values. So what's going to happen? Well, you know, the first write is going to succeed. So we're going to have 10, correct? And then that's it, right? We crash. So the value of b, you know, stays the same. So after a crash, like right here, that is going to be the state of our disk, correct? And so computer crashes, you know, like right between here. Computer comes back up. And what we have on the disk is these values 10 and 30 as we come up, right? And so now the bank application gets to run its recovery procedure. But, you know, the bank application and the recovery procedure has absolutely no information to decide whether this was actually a crash during a transfer, or a crash before the transfer, or a crash after the transfer, right? And so there's like nothing it can do. I think this is like the scenario where we sort of worried about a lot yesterday. You know, what do we do? And so the answer is that just basically update in place is just the wrong solution to actually implement transfer. And you have to implement it in a different way. And so the application has to be prepared that it actually might be a crash. And these implications, you know, what we need to do is actually think harder about actually how to implement write. We probably should not call the write function that directly updates the disk, and we need to do something else. Okay, so, well, what are our options? Well, it turns out there's sort of basically two broad approaches to solving this problem. So the better plan and this is what any database or, you know, for sort of a reasonable sophisticated file system actually implements. One of these two better plans, and basically it is never update in place. Because you think about it, you know, this update that we did in place basically destroyed any information that we had, you know, that A previews might have had. And so there's no really way for us sort of to roll back and roll forward to a correct state. And so the basic rule, you know, in these sort of crash-safe systems is don't update in place. And instead, you know, there's two ways of doing it. Sometimes it's called, you know, one is called shadowing, and the other one is called logging or journaling. Okay. So I'm going to summarize very quickly what shadowing is, and then I'll talk a little bit more about logging, which is what sort of more sophisticated systems will implement. So in the case of shadowing, the story is pretty straightforward. What we're going to do is, you can think about it, is that we're going to have two, we can have a file, basically, which has two blocks in it, this 10 and the A and B. We're going to also have a second file, which has A and B in it. So we have our bank state, you know, there's going to be an A and a B in it. And this is like our database with information. So database 1, there's database 2, also has, you know, a copy of A and B. And you can think, the way you think about it is that on the disk, you know, there's just not one copy of A and B, there's the two of them. You know, there's 10, these guys, here's the 1030 case. Let's start out with 20. Let's start out with the correct case, and it's a 2030. Correct? So what we're going to do basically is we're going to have two copies of everything. And now the story is pretty straightforward. Right? If you want to implement, you know, the first write, you know, it's going to go ahead and it's going to update the first copy. So let's say, you know, we succeed and we get to 10. Right? Now we update the, let's say B, we update the second one, so we're going to get to 40, and we sort of succeeded, right? And now we have the old version, the 2030, and the new version, right? So somewhere we need to record, you know, which actually is the current version. And so typically the way this works is that we typically annotate these pieces of programs a little bit and make them sort of transactions. So this is going to be a very simple transaction. We're going to have an operation called commit that basically tells, you know, the library that we sort of are implementing, the journaling system or the shadowing system, that we're done. You know, no more writes are coming. And so at this point, you know, we have our a piece of information. We have DB1 and DB2. You know, what we can do is to say, like, well, we can update and basically record that we should switch to the new version. So we can take one disk block and basically use that to indicate what is the new version and what's the old version, correct? So let's say, we label this, whatever. This is was 1, this was 2, and so before we start at 2 was the current version. We go row 3, write 10 and 40, and then we do a commit, and the commit point will write down what actually the new version is. And so in this case, that will come back, we go to version 1. Okay? And the fundamental assumption here is that a single disk write, a single block write, is an atomic operation. And so it will, the block that contains 2 will atomically contain a new piece of information, namely 1. And it's not going to have a bunch of bits in it that may be 1.5, like it wrote half of the block. There's an assumption that the disk writes the block atomically, and that most disks actually do. And exactly for this reason, because they need to support the applications like this. And so one way to think about this is, this commit atomically switches from the old version to the new version. Does that make sense? And this is a standard technique. Like your editor, most of your editors will implement it, correct? When you start editing, you actually don't edit the file that's directly on disk. Instead, the editor makes a copy, and you edit the copy, and the point you hit save, right? You actually call basically commit, if you will, and the file system has an atomic operation to switch the old and the new version. Typically, the rename system call under Unix, for example. Okay? And so this is basically the same plan as the shadowing plan, and it is very good and very useful. It has one downside, right, which you have to make a complete copy. When you start writing, the first thing you need to do is basically have a copy of the original version and work on that copy first before actually you make that copy visible. Now, if the copy contains 2 extra blocks, no big deal, right? Or it's a small file that you're editing, but there's like a terabyte database, that would be not so ideal, correct? Let's say like you're implementing Postgres or any other database, there's a terabyte of data in it. Before you actually start executing any transaction, the first thing you're not going to do is copy a terabyte to another place and start working on that terabyte, right? That is just not a great plan. And so the other plan is the logging plan. Right? So I'm going to describe that a little bit, and see, it works at the same sort of set of principles, namely never update in place. It will exploit the fact also that there's an atomic commit point, but it gives you a sense of like how real systems do this. Okay, good. So that's that. Let me see. I'm going to keep this and talk a little bit about logging. And we'll see that logging actually has a little bit of a more interesting recovery plan. And so when we discuss the recovery plan, we can actually talk about what is the crash conditions of recovery, what is the post condition of recovery if post condition succeeds, and so we can see how that sort of fits in this whole framework that we have been explaining to you. Okay? Yeah.
Can I ask one question about shadowing before we move on?
Yeah.
So it seems to me that there must be a little bit more to the story if you had more than 2 blocks.
Mm-hmm.
So you had some blocks that were not involved in the transaction. It seems like the commit would also have to copy the.
Yeah, the plan is, the way to think about it is there's some file, like in your editor, right? And that's the original file before you did anything. So that might contain, whatever, our original 2030, right? Or maybe a whole bunch of other state direction we're not touching.
I'm talking about the files that you didn't change in the transaction. That when you commit, it seems like you have to make sure that the state that you're committing to, whatever number you're setting that first block to, has to contain correct values for everything.
Yeah.
Not just for
That's correct.
things that you wrote in the
Yeah, so I think one way, actually, there's a point I wanted to make that I forgot to make is, one way to think about it is like a functional data structure. Where, we talked about functional B trees, correct, or red black trees, and basically, the game is, you're making basically a complete new tree, correct? You have the old tree, you have a complete new tree, and at the last point, you switch atomically the root. and that gives you the new tree. In some sense, this scheme is exactly the same, right? And it actually lines up with your sort of functional model because there's no writes in place. There's no update in place. Right? So it's just a pure functional. The way, the reason I, was slightly sloppy about this because I was sort of thinking about a file system where, it's clear, like, this file is being modified, all these files are not being modified, and there's an atomic rename, for just changing the one piece of the file that actually changed. And one way to think about that is if you have your functional, B tree, we're changing one leaf of the B tree, we replace that one thing, but everything else just stays the same, and we just inherit it.
You only make a copy of the bit that you're modifying.
Yeah.
And you're going to commit to at the end.
So thanks for that clarification. Okay, good. So any further questions about shadowing? It's sort of pretty intuitive, right? Okay, so what's the logging plan? The logging plan says, okay, here's our disk. And we're going to split the disk actually in two sections. We're going to have what I'm going to call the data section, which actually contains the blocks. So for example, it will contain A, it will contain B, etc. Right? And there's going to be a second section, where that's typically called the log or the journal. And it has to sit somewhere. It doesn't really matter where it is. I'm just going to put it at the front of the disk. And basically, what we're going to do, these, like as before, what we're going to turn these writes into, they're not going to be updating the write directly. They're going to actually call a function that our database is actually implementing. Right? So there's a stub. And the way the plan is very straightforward. When executing this function, what is this stub going to do? Well, it's going to write 10, correct? That was the first operation. But instead of updating A directly in place, as we now know is a bad plan, what we're going to do is just going to record in the log or in the journal that we need to change A to contain the value 10. So there's nothing is overwritten yet. You just make a record, that will actually that A needs to be changed to the value 10. Now let's assume for now there's actually no crashes. Yeah, go ahead. You want to?
So I was wondering, so this would actually be 2 blocks, I guess, if 10 is 1 block.
Yeah. So typically, okay. So let me be more careful. The way this works typically is there's a header block at the front of the log, and there we write in which blocks are being changed. And we might write here A, where there's plenty of space there. It's just a number, and then the value 10 would, for example, be the first block in the log. Right? And so now we have enough information space to store everything. So thank you. Okay, so let's assume everything, there's actually no crashes for a second. So now we're going to move on to the right. Our write stub, won't update, B directly because we know that's a bad plan, and it does exactly the same thing. We'll put in the header that we're going to change B, and we're going to put in the log, the new value for B, which I think was 40, correct? And that's it. Okay. So now, remember this is the commit point. And so now we executed the function commit. And the commit function, hold on a second. At the commit section, and we're going to basically reserve or write in the log, a block with C in it, indicating that it's committed. And one way to think about it, again, we're going to rely on the fact that this block is atomically updated. Right? So it's a single block, one disk write, and we're going to write basically, C in it, or like some flag to indicate that actually we committed. Okay? Yeah?
Even if you don't believe that your drive will atomically write, by putting proper checksums in, you can get the same effect. So you can always make the assumption that this is somehow possible.
Yeah. We're going to get back, actually, Nikolai will get back to this, depending on like how we're doing on time, on like sort of all kinds of assumptions. How can you relax them? How can you make them better? Were there any other questions? Okay, good. So, so now we're in pretty good shape. And we're actually succeeded in the commit. And the commit is now going to do one more thing, which is, since we committed, we're going to actually install these updates, because it's going to be completely safe. So there's going to be an install phase as part of the commit. And the install phase basically goes in the log and goes through the logs and puts everything in place. Right? And so let's assume everything works out perfect. And so what's going to happen? Well, it's going to take A. You know, you have enough information in the header to figure out where A is, put 10 there, and then put 40 there, and basically then clean up the log, because we don't need it anymore. Okay? So that is our sort of commit implementation. So there's 3 steps. 1, write a commit block. 2, install. 3, clean. All right? And we can all optimize this, but this is sort of conceptual what's going on. Yeah?
I think I missed something.
Okay.
So when we install the changes into the data blocks and we get a failure, then again we end up in an inconsistent state and we get more information to recreate original information.
Let me talk, and this was the next case I was going to talk about, which is namely what happens when there is actually a crash, right? And like what are all the possible cases that we need to consider. So let's do that. Let me make some little bit more space. And this all comes down to what is the crash condition, is recovery idempotent, et cetera, et cetera. Okay, so let me explain what actually happens in recovery. So I haven't really told you at all what the recovery procedure is going to look like, right? So what is the recovery procedure going to look like for our little database piece of software? Well, so we have a log, we have data, computer crashes, we'll come back up, we run maybe our replicated disk recovery procedure, and now the database gets to run its, its recovery procedure, right? And so, the database is going to look and say, okay, what does it have on disk? Well, this is the only information that it has, right? There's nothing else that it has. There's nothing in memory, there's no, because, the computer crashed. So the only persistent state is actually what it is here on the disk. And so the question is, is this sufficient, for us to get out of any mess? And, the mess that we want to make sure that we don't end up in, correct, is like the case where, A has 10 and B has 30, and we didn't actually, basically the economy is losing money, or money is just disappearing in thin air, right? Okay, so let's look at this. Well, it turns out we'll have enough information. The first thing, right, we can look at the log and decide actually, look for this, go for the log and find if there's, the transaction committed, right? So there's 2 cases. If committed, well, if committed, what should we do? Yeah, replay the log, right? We don't really know whether, when we crashed, did we crash, we know we crashed after writing the commit block, right? We don't really know if we wrote, we crashed, before install or after install, or, apparently we didn't crash after cleaning the log because otherwise, there would be no commit block in it. So we crashed, somewhere in here, right? And so we can just replay the log, right? And that should be totally safe, correct? Because if 10 and 40 were already there, well, the only thing that could happen is we write 10 to 40 again, right? And so if committed, replay log. Or install the log again, basically run install again. And then, presumably we can clean the log. So that we can start working on the next transaction that we do. Because we want to make sure that, if we start the next transaction, we don't have left anything in the log. Because if it crashes, then we would replay that again, but we already replayed it. And so just for convenience, it's better to, okay, good. What to do in the other case? We find no commit block in the log. Yeah, we're done, actually, presumably. The sort of cleaning the log is basically setting the commit button to 0 or, some event again. We're basically done. It must be the case that these 10 and 40 are the final values, right? Okay, so let's walk through this for a little scenario just to see actually whether actually things are hanging together. And so let's take our typical case. Here's our disk again. Here's our data. Here's A, here's B, here's our log. And here's our header. Nothing in it yet. No commit blocks, nothing. So the log. Okay, let's run through our program a little again. You know, we reread, nothing interesting happening. We do a write. So we're going to put A here, you know, 10 in the log. And the original values here are 20, 30, correct? And now we crash, because that's the one interesting case, right? And so if we crash, well, we have the right state, correct? The previous state actually on the disk. You know, this is before the transfer even started. There's no commit block. We just don't do nothing, because the log is just like not, you know, we can just start again at the beginning of the log, you know, for the next transaction. So that works out perfect, correct? You know, we don't lose money. And again, you know, let's say, you know, we get through to here, we get to 40, we write 40, B in it, we crash. Well, there's no commit block, nothing to be done. That's okay, because, you know, we still have a consistent, you know, the old version actually off, you know, the database is on disk. Now let's say there's a commit block on the disk. Well, then we run during recovery, we see it's committed, and then we install, and we actually roll forward, you know, to the two new versions, right? All make sense? So this is like the, if you will, the dumbest, you know, transaction system that you could write, but, you know, it gets the essence, you know, of what actually the transaction system does, right? And so this is how applications deal with writes. Yeah, go ahead.
Maybe I missed something, but how do you know that, like, you don't have garbage data sitting in your log?
Yeah, so there's hold that question. You know, there are a couple of ways of doing it. You can put a checksum in the first block so that you know what actually is in it. Actually, probably what you would do, you put the commit block, the commit bit in, you know, the header block, and you put some checksums in it so that you know that actually something valid. There's a little bit of a tricky story there, but.
So it seems like it's always going to be kind of a probabilistic thing.
No. Sorry, why? No. These are like, if the log, cleaning the log sets a 0 in here, right, and you read a 0 on the first block, you know there's nothing to be done. And otherwise, you know, there's some block in here where you wrote bits in it, and you parse those bits, and you know what they mean, and you just do whatever the bits are in there. And there's no probabilistic.
So we assume also that cleaning the log is atomic.
Yeah, well, we have to arrange it that the cleaning of the log is in it. Yeah.
But that's easy, because once you've removed the commit
Yep.
block,
The log is in.
you can remove all the rest
Yep.
at your leisure, and that's atomic.
Yep, correct. You know, just have to, the thing that always any of these systems exploits is there is some block that it can be atomically written, and sort of the switch from the new world to the old world, or from the old world to the new world, is at that particular block write. It's also typically called the commit point, where you switch from old to new. Okay, so let's you know, sort of, so this is like standard stuff. And so let's apply this, you know, sort of framework that we've been describing in the last, or at least, you know, informally apply that framework, you know, to you know, the things that we're doing here. So there's a couple of things we can talk about. So what is the crash condition of recovery? So if we had to write a spec, you know, for this recovery procedure, so, you know, previously we wrote a spec for the recovery procedure for the replicated disk. But now we're trying to write a spec, you know, for this, you know, the application level recovery procedure, right? And so, what should be the crash condition, or what would be a reasonable crash condition?
Either both writes succeed or both fail.
Yeah, although, you know, this recovery procedure doesn't really know whether we're doing 2 writes, 3 writes, 10 writes. You know, the transaction might be doing something completely different. Then, you know, it doesn't know really anything about transfer. I mean, that's the ideal sort of case, right? Yeah, I think that's a very good way of approaching it. Like so our file system FSCQ that uses the same sort of type framework and actually implements logging. Basically, its crash condition almost for all file system operations internally in the file system is one simple, you know, crash condition, namely, there's a valid log on the disk. And, you know, if there's a valid log in the disk, you know, it might contain a commit block, it might not contain a block, but it's at least valid. And that's the only sort of crash condition that we mostly carry through in the file system. Yeah, well, what is valid? Well, in this case, it means that the disk is split in 2 pieces. And the first part contains a log, the second part contains the data. And in the first block, there's a header that describes the log. And that's sort of our predicate that basically describes whether there's a valid log or not, or the assumption that we're making. Yeah.
It seems like the condition really wants the transaction you were trying to write the disk is properly preserved in the log, so that it's actually atomic and
Yeah.
succeeds
Yeah.
in happen. So how do we capture that? What were we trying to write?
You have to think of the abstract state. An abstract state for a logging system looks a lot like the shadowing system, where we have two copies of the world. So abstractly, you're running on top of this logging implementation, and you're thinking of a shadow. And at the commit point, there's some uncertainty: are you in the old or the new? And after the commit point, you know you're in the new.
Yeah.
And that's another part of this recovery condition that.
You can think about this. This guy has a spec too, correct? In fact, that is sort of the spec that we're implementing. And that spec is, its precondition is there's a valid database. Its postcondition, there's a valid database with A and B updated. Its crashing condition is there's a valid database with either A and B updated or not. Right? In fact, that is also its recovery condition. Right? Its crash condition is that there's the two cases the transfer can actually crash into. Okay. So the second thing we can ask is, intuitively, do we think that we can prove that recovery is idempotent?
As long as clean log's atomic, we get it.
Yeah. Right, we basically, we sort of already talked about this, and it seems clear that you should be able to rerun, if there's a valid commit block on the disk. If there's no commit block, there's nothing to be done here, correct? There's no question about idempotent, so it's certainly idempotent if you don't do anything. This is a little bit tricky, correct? Because you're actually modifying the disk. But, as we discussed earlier, it's perfectly safe, to replay the same value again and restore it in the place where we already installed it. So we're overriding the same block for the same block with the same value. So it should work out, right? So intuitively, idempotence, we should be able to prove idempotence for recovery. Okay. Good. Any questions about this? Okay, so we don't have a chance to give you yet another homework, but
We can do something after we leave.
yes, exactly. Well, you can finish all the other ones, but since we had a lot of time discussing this, here's a sort of free-throw exercise. Basically, implement a simple logging system on top of the disks that we've given you, or all the code we've given you. Write pre and post-condition crash conditions for this trivial logging system. And usually the framework that you have has enough machinery in it that you should be able to prove a post-condition for transfer that basically says A, B is updated or A, B is not updated. Right? And and we sort of already talked a little bit about what the crash conditions are going to look like. That in fact you have to prove that idempotent is that recovery is idempotent. And so this whole story of the crash post conditions, idempotence, and all that kind of stuff, the machinery that Nikolai just showed right before I started, applies equally well to writing basically this application in one level up. All right, so if you're excited about this stuff, then you can do it. If you just want to see how it actually works out in practice, we build a system called FSCQ, which is basically a transactional file system. So it has, in fact, it's like a POSIX file system. You can run, make-in on it and all that kind of stuff, but it is completely implemented using sort of this framework that we have described, actually a little bit of an earlier version of it. It has crash post conditions. You can look at it. And basically, so it's a file system for which we can prove, or this FSCQ comes with a proof that, written in Coq, that the FSCQ file system is crash safe. And that every system call either completely succeeds or doesn't succeed at all. You can run it on your laptop too if you want to. You probably don't want it to replace your default file system because it doesn't have enough features compared to what your default file system does. But you can look at the code if you would like to and play with it. FSEQ doesn't have, it has exactly the same sort of plan as we described, except the plan in the exercises is sort of made a lot more cleaner so that it's easier for you to do the exercises. Any further questions about this? Yeah, go ahead.
How does the performance look like for this?
Great question. And in fact, there's a good transition to what Nikolai is going to be talking about. We made a whole set of assumptions so far. And the first assumption that we made, or well, many, but one important one related to performance, is we assumed that the disk was synchronous. That if we do a write to the disk actually, when the write returns, that actually the bits are on the platter or on whatever, the non-volatile RAM that's sitting inside the disk. Turns out no disk works like that. What actually really happens is when you issue a write to the disk says, well, thank you for the bits, and puts it in its own persistent memory in the controller. And so it has its own RAM, puts it there, and then says, okay, thank you, bye, and returns, I did it. And of course, if you crash at that point, the power fails, the RAM will lose its content in the disk controller, and your block actually has not been written to the platter. And you may say, like, oh, that's stupid. And the reason is performance, right? Because it means that you can give a lot of writes to the disk, and then at some point the disk will say, like, oh, I got a lot of writes. Now maybe it's time to write things to a platter. And it can do all kinds of performance optimizations. And so, for example, it can take a whole bunch of blocks and sort of do one single sweep over the disk and put them in the right place. Or it can do absorption. If you write the 2 blocks twice, well, write it only once. And so there's all kinds of optimization. So this, if you write the file system on a synchronous disk, horrible performance. Factors 10 to 100 slower than if you actually exploit an asynchronous disk. But we haven't told you, how do you model an asynchronous disk, correct? And how do you model crash conditions then? And how do you model failure conditions? And so there's a whole other, that brings in a whole bunch of other interesting problems. And that's actually one that we solved. So, Nikolai, you want to?
Sure, yeah. So I guess
Yep.
There's another answer to the performance question. I guess there's 2 sources of performance overheads you might worry about. One is from design inefficiencies. So you're assuming too much from a disk, or you're doing things very slowly or synchronously, like the logging system that we just looked at. And those things slow you down quite a bit, because doing the wrong operation on a disk is super expensive, because everything on a disk is expensive compared to CPU time. And those are actually relatively easy to fix. You have to, well, easy in the sense that it's fairly straightforward what you should do. You should model the feature you want. You should implement the code and the logic that you think will give you good performance, and it'll actually work. So we have the version of FSEQ that you will find if you Google for it and check out the GitHub repo. Actually has a design that is perhaps slightly more sophisticated than even Linux ext4 in some ways, and actually gets, in some cases, better performance than the default Linux file system in terms of the disk I/O that it issues. So it's like a fairly clever file system in terms of the interactions with the persistent storage. The other sorts of overhead, the second thing you might worry about, is the executable code, so CPU performance. And there, you have to play a lot of tricks to get Haskell to generate code that's reasonable enough, and even then, you're probably going to suffer somewhat. So we've played a lot of those tricks in FSEQ, but we're not anywhere near ext4. Anywhere near meaning we're certainly, I would imagine, 10x-ish slower in terms of CPU overhead. But for many disks, it turns out CPU is not the bottleneck, so maybe that's okay. Or maybe not if you're using the CPU for something important at the same time. Make sense? All right. So I wanted to mention, sort of in closing, what are all the assumptions that we've been making, and what you might be able to do about them to either avoid the assumption or model something a bit more realistic, and how would you then structure your proofs and specifications and so on. So perhaps the most interesting one, or at least the one Franz mentioned, was the fact that currently in the assignments that we gave you, we had a model of synchronous disks. And what a synchronous disk means is that when a write operation returns, it is durable. And in particular, it means that if you crash after a write, the write will definitely be on disk. And what Franz described is reality differs from this model because there is a queue in front of a disk typically. And the write opcode is simply an insert into this queue on the disk's internal controller. And there's a separate operation called a barrier or a sink that asks the disk to flush its list of pending operations and return only after the entire queue has been flushed. So there's sort of three interesting things if you're trying to model asynchrony, this asynchronous write operation. So the complications, first off, is that this buffer is used for writes. Then you have to model the fact that there's a sync operation to flush the buffer. And the last and perhaps most sort of tricky thing to model is the disk can actually flush on its own. So you might think you put something in the queue and your abstraction says, yep, the queue has these three things in it. But while you're running, the disk will decide that two of those things are going to disk now. It's kind of a convenient time to write. And as a result, it is difficult for the sort of machinery that we presented to you so far to exactly reason about the state of the disk, because the state of the disk is changing underneath of you. At some level, this is similar to the model of concurrency that we looked at with background failures, where in a similar sense, the program running on the CPU doesn't exactly know what's going on with the disks until it looks. And at every instant, even if the program looked and the disk seemed to be okay, the moment after that, the disk might fail. So this requires us to come up with another, basically, special case handling of concurrency. And our sort of general plan in this whole FSCQ project has been to avoid, reasoning about full-scale concurrency so far and find clever encodings that allow us to manage limited forms of concurrency that show up, at least with this asynchronous disk. So this really leads to concurrency. And if you remember sort of the main plan we had for dealing with concurrency in the presence of failures was to use stable predicates to describe the state of the system. And if you use a stable predicate that isn't affected by concurrent background operations, then you can keep using these stable predicates without worrying about what's going on concurrently. So in order to start talking about predicates, we've got to find a model of some sort to represent the disk. So here's a model I'll propose to you guys. You can tell me if this seems reasonable or not, or if you think there's something missing. So in the synchronous world, the disk at an address has the type block. Or maybe in less Haskell-y terminology, a disk is a function from address to block, roughly speaking. Make sense? So that's our state, logically. In the async world, here's a model that I'll propose to you guys. We'll have disks be functions that go from an address to a non-empty list of blocks. And I'm not going to bother formalizing the non-empty part, but what I'm intending to represent with this list of blocks is this queue. The last thing in the list is the durable guy, so there's a list of blocks. This is what's actually on disk persistently, and this is the last write. So the model that you could have is that if you issue a write operation, it gets put at the head of the list. So here's a new write. And if you crash, you just get this guy. The rest of the list is discarded because the disk loses its volatile buffer. And if you sync, you sort of truncate the list this way. You make sure the last write is actually on disk and none of these guys are there anymore. Make sense? Yeah?
Why do you have to model the entire buffer? Why not just say the sync happens, the last thing we wrote gets on, and if you haven't done the sync, then it may or may not be on?
Sure, yeah, that's another model. The reason I'm choosing this model is that it will turn out to be a little bit easier to write stable predicates about it. So let's try to think about how would you state predicates about the disk in terms of this model. And then we can actually do the same exercise with another model and see. Yeah?
Isn't it also because the disk is free to flush like half of the queue? Because one is not on the major disk and you end up with something in the middle, one disk?
Right, so one possibility certainly is that you issued a write and it got appended to this queue. In the meantime, the disk was flushing something from the middle here that you wrote, and that ends up on disk. So you'd have to be a little bit careful in constructing with a model like what Sergio proposed, but I think it is doable. You could probably get rid of many of these things in the middle here, but you'd have to be a little bit careful to make sure it maps to reality. Yeah?
So this model does not, as it stands, cover reordering, but one would augment.
It does cover reordering because this is a buffer for every sector. So every sector has one of these buffers for writes to that sector. So this is sector 5. Here's sector 6. It only has 2 pending writes. Here's sector 7. You didn't write anything to it. It is stable. And the disk can independently decide which of these guys to advance with a background flush. When you sync all of them in the current SATA protocol, but there's forced syncs of individual sectors too. Yeah. Make sense? Question?
It sounds like this representation lost the ordering of writes to these different sectors, right?
That's right, and this is actually on purpose because the disk will reorder them for you, depending on what is more efficient for the disk to write to persistent storage.
But I would wonder, when you call the sync operation, would it have some semantics up to what point sync has?
Up to now. So the order of the sync matters with respect to all the writes. So everything that you wrote before the sync will be on durable storage when sync returns.
What if sync crashes? Is it a
Sync
problem?
effectively has a crash condition, which is exactly its precondition. So any way that you could have crashed before the sync are ways that you could crash during the sync. So one nice thing about operations that purely shrink the possible set of crashes is that you don't actually have to worry about them very much. They just shrink, so yeah. Another question.
Clean up all everything
in this particular case, sure. Let's say, yes, so there's a disk opcode that actually does push every sector to the last write, force every sector's pending writes to disk, yes.
And the CPU will be idle, waiting for the sync?
That's up to the CPU. Yeah, you don't have to, so certainly it could be idle or you could find something else to do in the meantime. Yeah, most operating systems find other stuff to do. Yeah. Another question?
Does the fact that the disk can also flush sort of autonomously give you an advantage once you think about several CPUs issuing write operations? Because sort of from the other CPU's point of view, sort of
so I think the model itself is not super helpful in that regard, but the use of stable predicates is helpful in that regard, which maybe is related, yeah. Absolutely. All right, so let's talk about predicates in the last few minutes that we have left here. So in the synchronous world, we used to state predicates of the form, the disk at address 5 has the value 20. So you could, in principle, state the same kind of predicate about the asynchronous world as well. You could say the disk at address 7 has the contents 8. So here's disk block 7 containing 8. That is a predicate. That is true. Is this one stable? Well, as it turns out, this one actually is stable because there's nothing else going on. There's actually nothing for the disk to do. So if a sector is flushed, there's no pending writes, it is stable because the disk has no freedom to modify it. On the other hand, if we have another predicate like the disk at address 6 has this list 2, 3, 4, and these are the blocks here, these guys turn out to be unstable because at any point the disk might switch from 2, 3, 4 to being just 2, 3. So if you write predicates of this form, you have to consider these executions of the disk concurrent with your code's execution on the CPU at every possible interleaving point, which is messy. And if you use stable predicates, you avoid this mess. And one way to state stable predicates for this model of concurrency is to use what's basically a prefix relation here. So instead of saying the disk at address 6 is literally 2, 3, and 4, which is unstable, you could say basically the disk at address 6 is a prefix. I don't know, I'll use the subset operator even though it's not entirely a subset. You could say it's basically a prefix of 2, 3, 4. And this turns out to be a stable relation because the concurrent operations of the disk only truncate things from the end of this list and result in a real state of D6 that is a prefix of what it used to be. So if you state your predicates about the disk in terms of these prefixes, you're in good shape. Well, at least you're in good shape in terms of pushing through the execution of your CPU code without having to consider the concurrent execution of the disk. Is this representation enough for you to do useful stuff?
You have to assume the list is not empty, right?
Yeah, that's right. Yeah. So you probably represent it as like a block, start list block or something. Yeah, exactly. Yeah. So at the very least, you have to do that. Yep. Any other thoughts? This is a good plan. Yeah.
What happens when you crash, though? Then
Yeah, so when you crash, now that's kind of interesting. Yeah, that's a good point. So before, we had a clear rule for what happens on a crash. On a crash, you get the last thing on a disk. What do you get when you crash in this state, when you don't actually know what the hell is going on? It's like you might get the 4, but maybe not. Maybe you get the 3, or maybe you get the 2 because the real disk advanced. So it's actually, this turns out to be okay because this models the real fact that after a crash, you don't really know if a disk got through your writes or not because you didn't sync them. So you actually have this real uncertainty about whether the disk really contains a 4 or really contains a 3 or really contains a 2. So on a crash, this representation actually captures roughly what you would want to capture, I think. Another way to think of it is, okay, would we be able to use this representation to reason about what the disk returns after a read? Is this enough? Yeah?
So I thought when this could crash, then you will, you couldn't get the 3 written in the disk.
That's right, yeah, 3 is a possible value.
2 will disappear. So
Yeah, in that case, 2 is gone and just 3 is there. So, of course, so that's right. So, yes, I should be perhaps more precise. These predicates are stable with respect to concurrent disk execution of background flushes. These predicates are not stable with respect to crashes. After a crash, something else happens. And we actually define a transformation on these predicates that basically says after a crash, what you have, so this crash transform says after a crash, it must be the case that D6 is a prefix of a single value x, where x came from this list 2, 3, 4. So you chose one of these lists, and now that's the thing permanently on disk, and there's no pending writes anymore. Yeah. So the cool thing about this representation that I want to come back to is the fact that it actually allows us to reason about reads and writes pretty easily. So writes still add to the head of this list, and that's a legit way to represent what's going on. And reads always return the value at the head of the list, because regardless of what's going on in the tail, maybe the tail got synced, the head doesn't change. So we'll be able to use this representation to reason about what a read from a disk must return. And now, yeah, question?
But is it actually, as it works, I mean, I would expect that when you issue a read and the buffer for that block is, there's something in the buffer, then you would flush the buffer.
Yeah, so when the CPU issues a read and there's a pending write in the queue, the disk will find the write and return the value back to you. So that's why I am saying that when you read, you will actually get the 2, which is the latest thing you wrote, and not 4, which might be the thing that's on persistent storage.
But then I don't get it. Why do you need to keep all these writes, since the one at the end will always overwrite anything that you have any other?
It will overwrite in the sense that if you wait long enough, it'll be durable. But you need to keep this tail, because this might be what's on disk when you crash.
Yes, but what is, in this case, 3? Why should we keep?
So 3 is a possible value that might be on disk when you crash. If it used to have 4, then you wrote 3, then you wrote 2. You might actually crash in all these different values now.
Right, but if you set up things in such a way that you only keep the
But the problem is that you don't know what's on disk. That is outside of your ability to reason about this stuff. You're reasoning about the CPU execution. The disk chooses what's on disk. In the background, you don't know what's going on there. So we're setting up this model that helps us reason about this uncertainty about what happened due to these background flushes.
Technical question, maybe for most people. Given the way the coalescing is done, you probably don't get deeper than 3 in practice on this, right?
It depends. It's somewhat less likely, sure, but
it's probably what's being written, the thing that has not yet been coalesced with in the most recent variety.
Perhaps, yeah. So there's certainly, for different disk firmwares, you'll get different behaviors.
Well, that's the reason that you need to reason about the full case.
That's right, yeah. So last thing I maybe want to say about this stuff is that it's actually very also easy to represent sync. So the effect of a sync is that you just truncate the list, and it transforms, it goes from D at address 6 maybe being some prefix of this list to just being a prefix of this very nice clean 2 list. So now it's, you know, everything is stable. You can reason about the crashes that always give you 2 after sync returns. And you can still use this stable version of a prefix predicate. Question?
So this is maybe a less practical way to do it, but if you could model the disk just as another program running concurrently, and basically all the writes would go through one such program for each sector, then you could kind of express it without special purpose modeling of the disk.
I think, yeah, so really there's 2 things going on. One is your lowest level model that you want to believe is accurately representing the physical world. And there's a bit of a gap here. We're basically saying pretend this fairly abstract way of modeling stuff is actually reality. So what you're proposing would be more faithful, because you would say, yeah, there's like 2 CPUs. There's a CPU here and a little ARM chip on the disk. It's got its own memory. It takes things from a queue. It got an algorithm. It writes stuff to disk. That is absolutely closer to the real world. And if you had access to this firmware and you wanted to verify, that's probably a good way to set it up. But even in that case, you would want to abstract away from those gory details and come up with an abstraction that helps developers writing code on the CPU to reason about what the hell is going on in this microcontroller. And in that case, I think this would be a reasonable abstraction. And I think it's reasonable regardless of whether you axiomatize it and say, this is my bottom level, trust me, or whether you prove that some implementation of a concurrent CPU here achieves this abstraction.
I think you may have been proposing something slightly different, which was not necessarily that you modeled a particular program there, but modeled this as a distributed system.
Oh, is that abstracting? Yeah. So you can go to different layers of detail. You could just say, yeah, absolutely, yeah. Another question back there? Maybe not. All right. So this gives you a sense of how you might extend the basic model we've been giving you guys in these homework assignments and labs so far. Our experience has been that the basic plan with these recovery conditions is actually enough to incorporate a wide range of sophisticated optimizations like these async disks. We have a little bit of some thoughts on concurrency we've been doing. Or we can incorporate checksum reasoning about collision-resistant hash functions. So many things can actually be fitted into the same overall framework depending on your desire to reason about a particular class of hardware features, execution semantics, and optimizations. Question?
So all the proofs that we've done for the replicated disk can be carried out with this model?
Yeah, you have to be, of course, a little bit more careful with recovery, because when you write to a replicated disk, there may be, the disks might have different background flush decisions, so you might actually have to use the sync opcode more, and you have to be a little bit more careful, but yeah, you can actually push it through. Sort of what I meant by your desire to actually push this through is that all these optimizations at the low level, or subtleties at the low level, mean that you actually have to write different code. You have to handle these different cases that now arise. But if you do so, it's actually doable to push the proofs through as well, then, in the same framework.
To preserve that importance of the crash state, in this case, if you're not careful, you could have differences in multiple steps.
That's right, yeah. So you could handle that in several ways. One is you could maybe change the abstraction and say you could have differences in multiple sectors because that's required for performance. Or you could use the sync opcode a lot and avoid the differences. And then you have really a trade-off. So real systems don't use the sync opcode a lot, and they expose an abstraction where you might disagree on multiple sectors, and then you have to fix up multiple sectors. Or in like real, if you buy a reasonably expensive RAID controller, or any RAID controller really, it has a battery backed up buffer that keeps track of the addresses that need to be fixed up, because it's expensive to scan the disk and compare, so most RAID controllers keep track of the outstanding addresses that have been modified, and then that helps them make the recovery more efficient without scanning everything. So many degrees of sophistication you could reason about here. All right, any other questions? That's all we had time for, and hope you guys enjoyed it.